Well, good morning or good afternoon or good evening, whenever it is that you're watching this. My name is Ben McCarty, and I'm over here at the University of Memphis in Tennessee. And I want to thank Micah and the organizers here for giving me the chance to speak to you in this format. We're going to talk a little bit about Khovanov homology for virtual links. And what we're going to talk about today is joint work with Scott Baldridge, Lou Kaufman, Heather Dye, and Aaron Kastner. Most of what we're going to talk about today is coming from a paper called Unoriented Khovanov Homology that I wrote with Scott and Lou, in which we set up a framework for computing Khovanov homology for virtual links. There's also the unoriented aspects that are in that paper. I'm going to say a little bit about that at the end, but if you're interested in getting a lot more detail on that, Scott Baldridge actually gave a talk in this same seminar last year. I would encourage you to go look at that and see what he has to say. He talks a lot about the unoriented Jones polynomial and applies it not just to virtual links, but to some problems in graph theory that are quite interesting. And then certain aspects of this talk are going to focus on computation of virtual Khovanov homology for virtual links, and for that part, Heather Dye and Aaron Kastner have been involved in a lot of that work as well. Though the paper on that work has not come out yet. We're still working on that. But before we get into this, there's a history here. So if you go back to the to the late 90s, Khovanov defined Khovanov homology as a way of categorifying the Jones polynomial. And so that paper that came out, I think it was in 1999, if I remember correctly. And it was a couple years later in 2001 or so that Bar Natan came out with his paper describing Khovanov homology, relating it to the Kaufman bracket, and built up a framework and actually wrote a program, a Mathematica program for computing Khovanov homology for classical links. So within 2 years, within a couple of years of Khovanov coming out with his theory, you've got a program for computing it that's been written by Bar Natan. You fast forward a few years to 2007, Manturov came out with what I think is the first paper that defined a way of a framework for defining virtual link Khovanov homology. And his framework, like I say, it came out in 2007. It took a while before we had a program. In fact, the first program that came out for computing Khovanov homology for virtual links was Tubbenhauer's in 2012. But his framework looks, if you go and look at his Mathematica code, he's published it online. His framework looks very different from what Manturov describes. It appears to be different. Whether or not it actually produces a different homology, I don't know the answer to that, but it looks very different. We didn't see a version of Khovanov homology for virtual links, a program for computing it, for quite some time. And as we're going to see as we go through this, I think the reason is because we needed several pieces of several advances to happen. And we saw those advances come out in 2014 with a paper by Dye, Kastner, and Kaufman, as well as some others that we're going to go through and talk about. And what we did in our unoriented Khovanov homology paper is we've taken these different results that came along in the 20-teens, and we put them together to produce this framework that has then allowed us to now, 13, 14 years later, produce a program that computes a version of Khovanov homology for virtual links that is actually what Manturov originally defined in 2007. And it is based on the code, or is derived from the code that Bar Natan originally wrote in the early noughties, around 2001 or so. So that's the overall story here. We're going to get into that. We're going to start with just a review here for the time being of how we get Khovanov homology for classical links, and then we'll veer off into looking at virtual link. All right, so here's the hop link. If you'll recall, the bracket polynomial is given by these two relations, the recursive definition here. We've got A smoothings and B smoothings. Every time we do a B smoothing, we pick up this factor of minus Q that's going to show up. And every time we remove an unknotted loop, we're going to pick up a factor of Q plus Q inverse. Now, you could compute this entirely recursively, but often it's convenient to just resolve all of the crossings. And I'm going to organize these things in a way that's going to be suggestive of what's to come later. I've got here in the first spot that we're looking at the all A smoothing. In the middle two states, I have states with a single B smoothing, and then I have the all B smoothing at the end. And if you look at the contribution from this state, what we've got is Q plus Q inverse squared. For the middle two states, well, for each one of those, there's going to be a minus Q, and we've got two of them. And there's going to be a single copy of Q plus Q inverse because there's a single loop. And then for the last one, what we have is two B smoothings. So that's going to give us a minus Q times a minus Q, or Q squared. And then we have Q plus Q inverse squared. Now, this is the Kaufman bracket. And so if you remember, the approach that you can find at Barnaton describes this. One approach is to essentially categorify the Kaufman bracket. And since the Kaufman bracket is up to a normalization factor, giving you the Jones polynomial, or you renormalized it, you multiply by a factor that depends on the ride, you can get the Jones polynomial from it. If we get a homology theory that categorifies the Kaufman bracket, we can then do grading shifts to produce the Khovanov homology. And so our idea is going to be, for this, to replace each of these states with a vector space, all right, where it's going to be a tensor product of copies of V, where we take we take the power, the K, be the number of circles, and our vector space is just going to be linear combinations of 1 and X. We're going to imagine attaching a label of 1 or an X to each of the loops in the state. Sometimes call these enhanced states, and using that terminology. And this is going to be more than just attaching these labels. We're going to have a couple of gradings associated to elements of these vector spaces. We're going to think of the 1 as having grading +1, and that corresponds to the exponent, the positive exponents on Q. So every time we see a 1, we should think of that as being corresponding to a Q to the first power. X corresponds to -1 and corresponds to a Q to the -1. And so the relationship between this polynomial and this vector space is such that, well, if I was to look at just the contribution to the polynomial from this first state, in this first term, I've got a Q squared +2 plus a Q to the -2. And that corresponds to, in V tensor V, corresponds to 1 tensor 1, X tensor 1, 1 tensor X, and X tensor X. This one has grading -2. Each of these has grading 1, grading 0, Q to the 0 power. And each of these this one has grading 2. Now, let's go ahead and look at what the calculation would look like here. As we just observed, I've got an X tensor X here. I've got a 1 tensor X and an X tensor 1, and I've got a 1 tensor 1 sitting here. In the middle column, well, before we get to that, that's those 4 elements generate what we're going to call C0 star of D. We're going to think of this as V1 tensor V2, where the subscript on the V is just indicating that it's a copy of V that goes with the first circle and the second circle. We're going to think of these circles as having an order here. Now for the middle column, for C1 star of D, well, that's just going to be V plus V. So if you remember, if you look at this, for every B smoothing that gets done, we pick up a copy of a factor of minus Q. And what that's going to do is that's going to effectively, since Q to the 1, that's giving us information about gradings of the elements. That's indicating that there needs to be a grading shift as we move from one column to the right. So X normally has grading minus 1, but with the grading shift accounted for, an X would go up here. And I've got 2 different states to account for. So I'm going to get 2 copies of that. And then similarly, 1, 0, and 0, 1. And then finally, for C2 star, this is again a copy of V1 tensor V2, circle 1, circle 2, like that, for instance. And there I'm going to get an X tensor X shifted up twice, because I'm 2 columns to the right. And then I have a 1 tensor X and an X tensor 1 and a 1 tensor 1. All right, so I've got these 3 columns, columns 0, 1, and 2. That's what we call the homological grading. I've got elements ranging from a quantum grading, a J grading, a vertical grading here of minus 2 up to all the way up to 4. That's all well and good. I've got all the linear combinations of these things that you would get, but I don't have a differential yet. So we've got to define a differential here. Now, if you think about what can happen when you change a single smoothing site from an A smoothing to a B smoothing, there are really only 2 possibilities. You can either take 2 circles and merge them into 1, or take 1 circle and split it into 2. If we look at what happens here, well, if we look at these 2 maps, those are both what we'll call merging maps, or multiplication maps, as they're going to also be known. And then these 2 will be splitting maps or co-multiplication maps. So let's look at what our differential is doing here. For the multiplication maps, for the merging maps, the multiplication is going to correspond, the map is going to correspond to multiplication in the vector space V. So X tensor X would go to X squared, but we're modding out by that, so that's 0. So this guy's in the kernel. And since there's nothing in homological grading minus 1, that's a homology class. We look at these 2 elements, the X tensor 1 and the 1 tensor X. Well, those multiplications both take us to X. So this guy is going to go to the sum of these 2, as is this guy. That means that if I look at the difference between these 2 elements, since there's nothing in homological grading minus 1 to hit it, that's going to be a homology class. And then 1 tensor 1 similarly is going to go to 1, 1. We go to the co-multiplication maps. Well, that's defined like we see here. 1 goes to 1 tensor X plus X tensor 1, and X goes to X tensor X. So these 2 gadgets go to X tensor X. Now, the difference would be in the kernel, but that's before we consider the fact that there's going to be a sign that we haven't dealt with yet. And that sign convention comes from looking at, well, if we think of this as the all A smoothing, this is the, see, the BA smoothing, this is the AB smoothing, and this is the BB. The usual sign convention would put a negative on this edge right here because there's a single B smoothing before the A smoothing that we're changing. So with that in mind, then with that negative in place, then the sum of these two would be in the kernel, but the sum of these two is also in the image. If we look at 1, 0, that goes to the sum here, or rather the negative of the sum, I should say. And this one does the same. But again, the same sort of thing's going to happen. You can get an element of the kernel from these two, but it'll also be in the image. And then everything in homological grading 2 is in the kernel, but well, x tensor x is in the image, and the sum of these two is in the image, but we take just one of them, that'll be a homology class, and as will this. So for this, we get we get homology classes in these 4 locations. So we're going to have a copy of the integers at grading 0, -2, 0, 0, 2, 2, and 2, 4. Okay, and if you play with this bracket polynomial that we just computed, expand everything out and simplify, you'll see that we'll get q to the -2 plus 1 plus q squared plus q to the 4th. Okay, so that's in a nutshell how we get the bracket homology. The bracket homology is just the homology of the complex that we've just built. And it's a theorem going back to Khovanov, that the homology theory that we want, that's actually invariant, an invariant of the link, invariant under the Reidemeister moves, is this bracket homology shifted, and I'm using Bar-Natan's grading shift notation, shifted by the number of negative crossings in the homological grading, and this term n plus minus 2n minus in the quantum grading. So that's all for a classical link. Question then comes up, why can't we just do the same thing for a virtual link? So virtual links have classical crossings. They also have these virtual crossings, but we essentially treat them as though they're not there. So why not do the same thing? Just take the classical crossings, resolve them into A and B smoothings, compute a bracket polynomial as you normally do, ignore the virtual crossings, and then I create homology theory out of that. Well, we run into problems, as you might guess. Here's a 2-crossing virtual unknot. Okay, and well, we can go ahead and start filling in try to do the same thing. Let's, to each of these states, attach labels of 1 and x, and try to build a vector space, or try to build a chain complex. For this first state, there's only one loop. So I'm going to get a copy of x and 1. In the middle column, I have a single loop on top and 2 loops on the bottom. Let's take care of the 2 loops first. So let's call this loop 1 and loop 2. This will be, once we shift up once, this will be x tensor x, 1 tensor x, and x tensor 1, and then 1 tensor 1. For the single loop, we're going to have just an x and a 1. Again, when we shift up once, we put an x here and a 1 there. And for the final state, we have a single loop. That's going to give us an x and a 1, like so. Now on the bottom, we have a delta map, a co-multiplication, and a multiplication. Along the top is where things get different, where things change. We have a single loop going to a single loop. Now that can't happen in the classical case, but it can happen in the virtual case. We're going to label that as an eta map. It's neither a multiplication nor a co-multiplication. Now the question immediately arises, what can this eta map be? We'd like to keep M and delta the same so that the Khovanov homology for virtual links, when you feed it in a classical link, it gives you the same answer as it did before. So what can eta be? Well, if we just take into account the fact that, if you remember, when we computed these differentials for the classical, the Hopf link, the differentials preserve the quantum grading. They always go straight across. They increase the homological grading by 1, and they preserve the quantum grading. This is a general feature of the differential in when you take a classical link, looking at the Khovanov homology for a classical link. We'd like that to still be true here. But when you look at the elements that correspond to these two states that have one circle, well, the grading shift makes it so that they don't line up. So if we want the differential to preserve the grading, eta has to be the 0 map. Okay, so that we can make that choice. Then the question is, well, before, one of the things that happens is that when you look at the way those two maps are defined, essentially every possible 2x2 face of the cube of resolutions, if you will, automatically will commute with those definitions of M and delta. So is that true? Is that true here? Well, let's say we have a 1 attached to this first state. We map it up here, we're going to get 0. We map that on, of course, we still get 0. When we map it via delta, we get 1 tensor x plus x tensor 1. I'm ignoring the sign convention on these edges for now. Let's not worry about that. But then this goes to 2x when you multiply. Now, there's no sign convention that I can use by sprinkling signs on the edges on the local differentials here on the M, delta, or etas. There's no sign convention I can do on those edges to make that face commute. This is a problem. Now, it's not a problem if you were working over with coefficients in the integers mod 2. If that were the case, then you can actually just define eta to be 0, keep M and delta as they were before, and you'll get a homology theory with mod 2 coefficients. If you want to get integer coefficients, you're gonna have to deal with the fact that this face doesn't commute right now. So what do we do? Well, if you look, we kind of want one of these terms, this, at 1 tensor x and x tensor 1, we'd like for one of them to be negative, so that when we map it over, we get x minus x, and it's 0, and everything's lovely. So we need a way to do that. We need a systematic way to do that. And this was described. I'm going to look at the description that Kastner and Kaufman gave in 2014. They're implementing something similar to what Mantarov did in 2007, but their description, I think, is useful to look at here. We're going to use a source sink orientation to produce our sign convention. Now, the way this works, first we pick an orientation on our knot, our link. All right, so let's assume our orientation is flowing up through the crossings like this. Now, if the classical crossing is oriented with the arrows going upward like this, we're going to insert a source on these arcs, and it's going to be act like a sink on those arcs. And similarly for this crossing. We just do this at every crossing. And then if you look, well, on this arc, the source sink orientation, the red orientation that you're getting here, is consistent. Along this arc, it's consistent. But along this one, it's inconsistent. So we're going to put in a cut point right there. And same thing happens over here. So we get 2 cut points like that. We'll get a cut point on each of these states. And then we're going to pick a base point somewhere on each of the states. So I'll pick my base point to be here, here, and I need a base point on this circle. I'll call that C1 and C2, say. And then I'll take the base point to be here and here. That choice is essentially arbitrary. Now, what do we do then? So this is, remember, this is an eta map. So is this is a delta, and that's an M. So what we're going to do is we're going to place our element of the vector space at the base point. And well, we know already that's going to go to 0 along the eta map, so we won't worry about that right now. But going down here along these bottom two arrows, I'm going to transport the 1 to the site where the smoothing is to take place. I do that here, nothing happens there. If it was an X and it passed through a base point, I'm going to switch the sign, but here nothing happens. So I go to put a 1, I perform the map, that 1 goes to a 1 tensor X plus X tensor 1. Now I've got to get the algebra up to the other smoothing site to perform that map. So here I'm going to transport this up. This is going to become 1 and X there. But this one, these, to get up to the smoothing site, pass through a cut point. Now nothing happens to the 1, but the X picks up a negative when it passes through the cut point. And that's going to be the convention that we'll use. We're using these cut points to determine when we're going to place a negative on the X. Every time it passes through a cut point, it picks up a negative. In Die-Kastner and Khovanov, they describe this as a barring operation. So something like conjugation, if you will, where the 1 doesn't pick up a negative, whether you pass through a cut point or not, but just the X does. However you want to talk about it, we're picking up a negative every time we pass through a cut point, just on the X's. Now what that has, the impact of that is that then when I multiply, I get X minus X, which gives me the 0 that I want on the final state. So now this face commutes. It turns out they go through and they prove that this convention will fix this issue. All right. Now it doesn't fix everything. Now to see that, let's look at another example. So I've got here a virtual Borromean rings kind of link. And I've drawn here one particular face of those Borromean rings. And what I want to look at is what happens when we apply this same sign convention to this face. So let's assume we're starting with let's start with a 1. And let's go along the top 2 edges first. So along the top, we're changing initially this crossing, this smoothing to that. So I'm going to transport this over. That becomes a 1 right there. And these are 2 circles. So this is going to be a 1 tensor X plus X tensor 1. And now I've got to change this site, this A smoothing to that B smoothing. So I've got to transport the algebra over. It passes through a cut point. I'm going to get a minus X and a 1. And here, it also passes through a cut point. So I'm going to get a 1 and a minus X. So when I map it over, I end up with minus 2X here. And when I transport that back to the base point, it passes through a cut point again and becomes 2X. Now, let me switch color. Going the other way, I transport it over. it's going through a cut point, but it's a 1, so I'm not going to do anything to it. I'm going to get a 1x and x1. And now I have to transport things to the other site. That becomes 1 and minus x, as does this, minus x and 1. So this becomes negative 1 tensor x minus x tensor 1. When I map it over, I get minus 2x. But now when I transport it back to the base point, I get minus 2x. So with this sign convention, what we're seeing is, okay, we've fixed the eta face that we saw before, right? We fixed this face, but at the expense of making it so that sometimes our faces are going to commute, like this one commuted. Sometimes they anti-commute. That's a problem. So the strategy, remember, with Khovanov homology for classical links, the idea was, with the definition of M and delta as they are, every face commutes. And then there's this standard recipe for putting signs on the local differentials in your cube of resolutions. And that makes everything anti-commute and everything's lovely. Well, now with our sign convention that we've got some faces that are going to commute, some faces that are going to anti-commute. That's going to be a problem. All right. Well, they have a solution for this. Dicaster and Kaufman give a solution or a description of a solution that it's very much like what Mantarov did in 2007. And well, actually, we're going to use sort of something that use elements of both to talk about this. So, yeah, for classical links, there are no cut points. Everything's going to commute. But with virtual links, you can have commutative or anti-commutative faces. Dicaster and Kaufman talk about local orders as a way of getting around this problem. And the local orders basically look like this. If you orient the link, so the arrows that I've drawn here, these purple arrows on the link, this is an actual orientation, not a source sink orientation. So an actual orientation of the link. You look at the crossings, and we're going to whenever you have a smoothing, so you have a smoothing like this, if there are two different circles there, we're going to treat this as locally being the first circle, and this is being the second. And if the smoothing goes this way, the one on the left is the first circle, and the one on the right is the second. Now, all along, we've been using a global ordering of the circles, right? Every time we have two different circles, I've been labeling a circle 1 and a circle 2. We automatically have to have that because we have to have a way of identifying when there's a tensor product of x's and 1s. We've got to identify which label goes with which circle. We have to have a way of identifying that, and so we have to have some order that we're writing things in. So there's a global ordering of the circles. What Dicaster and Kaufman are defining as a local ordering, where if you just look at the crossing, there's a first and a second that may or may not agree with the global ordering that you've chosen for the circles. Now, the way this is going to work is, well, here, let's look at this first smoothing that I have, where I only have a single, or this first state that I have, rather, where I only have a single circle, single loop. This delta map that goes up and to the right goes to a state with 2 loops by changing this crossing, this smoothing from an A to a V. Now, if you remember, the arrows on that smoothing go sort of down and to the right, which means that over here, the arc on the left is this one. That's going to be labeled a 1 locally, and that's going to be labeled a 2 locally. Notice that doesn't agree with the global order. That's a sign that we need to put a negative on that edge. That's how they're going to determine this. Similarly, when we get over here, remember the orientation is going up and to the left at this crossing. So this is a 1 and this is a 2, locally speaking. So when we map that over via this merge map, well, that's going to pick up a negative there. If we go along the bottom two edges, we go along the bottom two edges. Well, now we're changing that smoothing site. And again, the arrows are going up and to the left here. So the locally, the first circle is this one, and the second one is that one. And that agrees. So we're not going to put a negative there. And then similarly, this will be the first, and this will be a second. And so it agrees there. So we're not going to put a negative on that edge. Now, if you remember, this is the same face we were just looking at that was anti-commutative. The sign convention that they've just defined, or that we've just looked at, preserves the fact that it's anti-commutative. The question is going to be, what's going to happen? What's going to happen when you feed it a face that was commutative? We want to see, hopefully, that it makes it anti-commutative. And we'll see that in just a second. Before we get to that, I want to describe a little more generally what's happening, because it's all well and good with two circles. What happens if you've got a whole bunch of them? And for this, I want to describe, Mantorov uses this wedge product construction that I think is really useful for describing how to get the sign. So we've got a global ordering of the loops in our state. And let's suppose we're changing this smoothing here from an A to a B. That's going to be a merge map. It's going to merge circle 2 and circle 5. So Mantorov's, the sign convention that he describes says, okay, let's suppose we've got C1 wedge, C2 wedge, C3 wedge, C4 wedge, C5. First thing we're going to do is we're going to take the two circles to be merged, and we're going to move them to the front of the list. So this picks up a negative, and then I'm going to take C5, and it's going to hop 1, 2, 3 times. So this is going to go to C2, wedge, C5, wedge, C1, wedge, C3, wedge, C4. There's a total of 4 transpositions, so it's still going to be positive. Then we're going to perform the map. We're going to perform the multiplication. When we multiply, we're going to keep the label that's the smaller of the two. And so we'll keep the label of the label of C2. So we're going to have C2 wedge, C1 wedge, C3 wedge, C4. And here I've assumed, I didn't say this, but hopefully you see it from the headline here. Here we're assuming that the local order, as we just described, agrees with the global order. So if we look at this, this will be circle 1. The label here would be a 1, and the label here would be a 2. Right? So in that case, we would just perform the map, and then we need 1 transposition to move C2 into the correct position indicated by the global order. And so we get C1 wedge, negative C1 wedge, C2 wedge, C3 wedge, C4. Now, if the local and global orders don't agree, the process looks the same. We still end up moving the 2 circles to the head of the list. But there's one additional step to swap these 2, to transpose C2 and C5. So that's going to pick up a negative here. Oops, C5 wedge C2. When I map that over, I have negative. I'm still going to keep the smaller label, C2 wedge C1 wedge C3 wedge C4, running out of room. And then I still have to do a transposition to move C2 into the correct position indicated by the global order. So that's going to be a C1, wedge C2, wedge C3, wedge C4. So this is how you deal with the signs when you have lots of circles floating around. We're still comparing the local and global orders ultimately, but we're using the global orders to track the signs on these edges, the local and global orders to track the signs on these edges of the qubit resolutions across the board. We've already seen that at least in the example we computed that anti-commutative face stayed anti-commutative. This commutative face, right? This is the Hopf link. Automatically, the faces are going to commute. We see here that if we compare the local and global, circle 1, circle 2, we have agreement on this edge. We have disagreement on this edge, so that's going to pick up a negative. Here we have, after the fact, we have agreement and we have agreement, so that's the only negative we pick up. We pick up just a negative on one of those 4 edges, so it's made anti-commutative by using the sign convention. Now, obviously, we haven't proven anything here. It takes a little work to do this, but Dicasner Kaufman proved back in 2014 that with these sign conventions, the sign convention coming from the cut point system that changes signs within the terms of a given within a given linear combination of tensor products of 1s and x's. Within those terms, it can change the sign, plus the local global order sign convention that we're describing that changes the sign on the actual local differentials themselves. They proved that all faces of the bracket complex will commute, or sorry, anti-commute, not commute. So this gives us a setup, a way of having a computing Khovanov homology for virtual links that looks very much like what Manarov did in 2007. It's sort of it's a nice way of describing it. Now, if we want to tell a computer how to do this, we've got to somehow give it all of these choices. Now, if you go back to Bar-Natan's original program, he uses planar diagrams for the links as his way of inputting a link. Now, a planar diagram still makes sense for a virtual link. The way this is going to go is essentially we're going to label the arcs of the link with numbers. So from classical crossing to classical crossing. So let's say this is arc 1. That means that arc 1 is going to end here. Treat the virtual crossing as though it's not there. That's a 1. Let's say that's a 2. That's still 2. Here's 3. That's 3, 4, and 4. And then we're going to go to each classical crossing and we're going to record a 4 tuple starting at the incoming understrand. So there's clearly an orientation here. If we just go in numerical order, 1, 2, 3, there's clearly an orientation on these strands, 3, 4, and then loops back around to 1. So starting at the incoming understrand, we're going to go counterclockwise around the crossing. So 2, 4, 3, 1. And then for this crossing, we're going to go 1, 4, 2, 3. And that set of 4 tuples is what we're going to call our PD notation, our planar diagram notation. Similarly for this guy, notice in this first example, there was by putting the arcs, the labels on the arcs, there was clearly an orientation given by the code itself. I want that feature to be preserved because I want to be able. When we write Mathematica code to do this, we're going to want the code to be able to look at a crossing, and in order to place cut points and compute local orders and all this stuff, we're going to want to know what the orientation is from the code itself. Now, if you look at this little link here, I've put in these Reidemeister 1s on. Whoops. on the on a couple of the arcs, because if they weren't there, and I was to label this arc as 1, if that wasn't there, then this would also be a 1 up here at the top. And I'd only have 2 arcs on that component of the link. And if you think about it, if the arc's labeled just 1, 2, 1, 2 going around, it's labeled 1, 2, there's no way to choose to figure out an orientation from the labels on the arcs. So that little Reidemeister 1 there is in place to ensure that when I label my arcs like so, I can look at this crossing and know that that's oriented from 2 to 3, from 1 to 2, and here from 3 to 4 and 4 to 1, because that's where it's looping around. All right, so that's the explanation for those little Reidemeister 1 moves that we put in. And then I'll label this a 5, that's a 5, and then 6, 6, 7, 7, 8, and 8. So if we look at the PD code, we're going to have, again, starting at the incoming understrand, that's 3, 4, 4, 1. And then 2, 7, 3, 6. And then 1, 6, 2, 5. And lastly, 7, 5, 8, 8. So, claim here is that the PD notation that Barnaton was using way back in 2001 already has enough information about the link. If we make this convention that we're going to put in, say, a Reidemeister 1 little stabilization move, so that the PD notation determines an orientation, it contains everything you need in order to get all of the stuff that Mantorov and Dykastner-Kaufman are saying you need in order to define a virtual Khovanov homology. Now, we're going to have to be a little bit clever because some of those choices, some of those auxiliary structures, we're going to pick different conventions than Dykastner-Kaufman did, different than Mantorov did, and we're going to need some other results that have come along in recent years in order to say that those choices that we're going to make actually are still giving us the same homology theory and not something else entirely. So let's look at how we get those choices first of all, and then we'll talk about where some of the results come from that say that these choices are still giving us the same thing. So let's start with the base points in the global orders. We'll talk a little bit about the code here, but let's think about how we're going to get how we're going to do the smoothings and how we're going to get the base points in the order. So yeah, if we look at this, I've got a function here called state to circles. This is a variation on a function that was actually in Barnaton's original program for classical links. You feed in a link in PD notation. You feed in a list that's binary. It's zeros and ones. 0 corresponding to an A smoothing, 1 corresponding to a B smoothing. The list tells you how you want to smooth the crossings. And what it does is it takes everywhere it sees a 0 smoothing, right? Everywhere it sees a 0 smoothing, it's going to put in 2 arcs, right? And IJ and KL. So for example, if this is IJ, KL, well, for the 0 smoothing, whoops, that's an L, and that's a K. For a 0 smoothing, that's going to look like that. So it puts in these 2 arcs, PIJ, PKL, and it keeps the smaller of the 2 labels from those arcs. For a 1 smoothing, it's going to put in IL and JK, right? And then there are these routines, these various arc merge routines that go through and tell the system to say, well, we've got this collection of arcs. They have overlap where I appears on this arc and then I is going to appear on this other arc on one end of it. Well, that's indicating that those two arcs should be merged to make a circle. So it's going to merge these things, and at each stage when it merges them, it's going to preserve the label of the smallest arc on that bigger arc that it's making. So in the end, what we end up with is a collection of, when we merge everything as far as we can, we end up with a circle. We end up with an arc of the form PII with the smallest arc label given by M. We're going to call that circle M. So what happens in the end is that you end up with, you smooth everything out, you go through this routine, you end up with the circles being labeled by whatever the smallest label that appeared on that circle was. So for this state, the smallest label that appears on it is clearly a 1. So I'm going to call this C1, and I'm going to put the base point, just by convention, I'm going to choose to put the base point in the middle of arc 1. Right? Same thing happens here, and same thing happens here. It's different here. This one still contains arc 1, so I'm going to put the base point there. But this one, if you notice, is made up of these two little pieces, these two arcs on the original link. The smallest arc label that appears on it is 2, so that becomes circle C2. So this process of merging of resolving and then merging the arcs at the ends and keeping the smallest label gives us a way to name the circles that we end up with, and it gives us a way to an obvious place to put the base point right on that smallest arc label, or at least it gives us a choice. We could have made a different choice, I suppose, but it gives us a choice that we can compute. We look at this example. So here's a particular smoothing for this guy. Notice that if we follow the same routine, we're going to get that this is going to be circle C4 with the base point on the arc labeled 4. Similarly, this is C8. For this big outer circle, that contains arc 1. So we're going to put a base point and call that C1. The smallest label on this guy is C2. Now, if you notice, whoops, yeah, okay. If you notice, the arcs, the circle labels, the names of the circles, 1, 2, 4, and 8, well, they skip over some stuff. But as far as determining a global order, I don't care that numbers are skipped. I know that 1 comes before 2 and 2 before 8 and 4 before, or it's like 2 before 4 and 4 before 8. A lot of 4s in that sentence. The point is this convention, this state to circles function is giving me both a way of identifying the global order and a way of picking out a base point. Our convention with in terms of putting in these Reidemeister 1s so that the PD code gives an orientation means that we can always locally look at one of our terms that looks like I, J, K, L, and know that the orientation goes this way on the I, from I to K. And by just comparing the values of J and L, as we see here, we can determine whether it's a left-hand or right-hand crossing. So we can get the number of left-hand and right-hand crossings. If you remember for the theorem that showed how to shift the bracket homology to get Khovanov, that's going to be important for us in just a minute. But it's also important in terms of determining the local order. If I can determine the direction of these arrows, I can know when I look at my smoothing arcs, which circle is 1 and which circle is 2. It is also important in placing the cut points. Now, this is where we're going to deviate from Dicastner and Kaufman. Dicastner and Kaufman, if you remember, at each classical crossing, they put a source sink orientation. And then they only put in cut points when the the source sink orientation is inconsistent on an arc. What we're going to do is we're going to put cut points on the left-hand side of every classical crossing. Now you could think of this as a source sink orientation, right? If it's going out here and in there, well, it's going out there and out there and in there. But it's a source sink orientation that is compatible with the original orientation of the link, right? It's the source sink orientation at the classical crossing, right near the classical crossing. But as you move away from the classical crossing past these little cut points that are placed close by, well, then the source sink orientation everywhere else agrees with the actual orientation on the link. Now this means that we're going to have a bunch of extra cut points that Dicastner and Kaufman didn't have, but it also means that we don't have to track a list of cut points. That's useful when you're programming this, right? It's entirely contained within the PD code what this choice is going to be. So even though this is a different convention, it's a different cut point system than Dicastner and Kaufman used, there's a notion of cut point equivalence that you can find described in a paper by Kamada in 2017, which allows you to move cut points past crossings and cancel cut point pairs of adjacent cut points. And so Kamada describes this notion of cut point equivalence, in which when you take two cut point systems that are equivalent, you're going to get the same sign convention that Dicastner and Kaufman got. And our cut point system is going to be equivalent to the one that Dicastner and Kaufman actually picked. In fact, you can see that essentially, if you follow this arc around and you end up coming into another cut point, those two cut points will cancel out. Dicastner and Kaufman would have never put them there, would have never put them in. But for our sake, when we're computing this in Mathematica or with a program, it's helpful to have them there. So these are all the conventions that Dicastner and Kaufman say we need, and what we've got are results that say that, well, we've made different choices in some cases, but turns out they're going to be the same. Actually, we have to say a little bit more about that in just a second, because we haven't. There's a little more that we'll say. But the homology theory that we're going to get, the Khovanov homology for a virtual link that we're going to get, is just the homology of this bracket homology. Take the bracket homology complex. So take the chain complex that we've just defined. So in other words, do everything just like you did for a classical link in terms of placing your generators for the complex and grading everything. You define eta to be equal to 0, and we're going to define our sign conventions both within the different terms of the local differentials and for the actual local differentials themselves, the signs on the edges of the cubic resolutions. Define them as we've described here, right? Take the homology of that complex, and that's going to be the bracket homology. Then shift that bracket homology in exactly the same way that we did for a classical link. That's what we're calling the Khovanov homology of the virtual link L. So that's it in a nutshell. Now, the paper that this is coming from, that Scott and Lou and I wrote, is called Unoriented Khovanov homology. Now, as I said before, Scott gave a talk on the unoriented aspects that goes into a lot of detail. I'll say a few words about this. So, before I get to the unoriented aspects, one more point. There's one final result that we need to talk about. That is due to Igor Nikonov, just just last year, I believe, that says essentially that when you're defining a homology theory for virtual links, there are all these choices that you're making. The choices of a cut point system, the choice of a global order, the choice of a of what you know, your convention for the local orders. The choice, you have all these different choices that you're making. Now, all of those choices might potentially matter, might potentially change the homology that you're going to get. What Igor showed is that when you change any one of those structures in a certain way, that the homology that you get doesn't depend on the choice of those structures, up to possibly grading shifts. But then those grading shifts, are going to be accounted for later. In fact, it's just stronger than that, right? That the homology theory that you get, if you change things like the cut system, right? You pick a different cut system than what we did, or than what Dicastor and Kaufman did. That in fact, that's not going to change the homology. So the point here is, the takeaway here is that yes, we're making lots of choices, but in some sense, those choices that we're making, we can make those choices in various ways. We still know that we're getting the same homology that Mantarov was describing way back in 2007. Because that's the takeaway. Now, how is it unoriented? Let's talk a little bit about that before we wrap up here. The bracket homology, just like the bracket polynomial itself, well, in fact, the bracket polynomial itself is clearly independent of orientation, because you don't ever have to pick an orientation at all to define it. The bracket homology, as we've defined it, we do have to pick an orientation to define it. But one thing we showed in our paper is that up to a grading shift, the homology that you get is independent of the orientation. So you can change the orientation around. You're going to get you may change the you may change the number of positive and negative crossings. You may change where they are. All that's going to do is potentially do a grading shift, and that's not going to change. Once you shift everything according to a certain prescribed choice that we'll talk about in a minute, it's not going to change anything. And then there's a particular shift that you can do, a particular grading shift that you can do to the complex to get what we call the unoriented Khovanov homology. All the definitions work just like they did in the talk so far in terms of computing the bracket complex. So again, this is still the chain complex for the bracket homology. We're going to shift that in a particular way. The shifts depend on the number of negative self-crossings. By self-crossing, I mean where a single component of the link, a crossing that involves only a single component of the link. A crossing that involves only a single component doesn't depend on the orientation of the link, because however you orient that component, the self-crossings don't change from positive to negative or vice versa. It also depends on the number of mixed crossings, which we're labeling as M. Those are the crossings that can possibly change sign depending on how the orientation changes, but the number of them doesn't. And so, you know, you can to see a description of where these two grading shifts are coming from. Go look at Scott's talk. He derives both of these shifts there in terms of talking about the unoriented Jones polynomial. And well, if you take the complex and shift it in this way, these two shifts don't depend on a choice of orientation. And you get a complex then that gives you a homology theory that we're calling the unoriented Khovanov homology, and it's independent of the link orientation. The graded Euler characteristic of that of that complex, of that homology theory, is one possible candidate, one possible definition for an unoriented Jones polynomial, which we call JL0. It's not what we ultimately defined as the unoriented Jones polynomial, but it is a polynomial that is a lot like, looks a lot like a Jones polynomial. Depends on it's the bracket polynomial up to this extra factor that depends on these grading shifts. But yeah, go look at Scott, go watch Scott's talk if you want to know more about that polynomial. I want to close with a few questions, a few results that we still have. The first question is maybe an obvious one. So this all comes from the framework all comes from a paper that Scott and Lou and I wrote called Unoriented Khovanov Homology. Now, clearly, the bracket homology, as we've defined it, depends on choosing an orientation, even though you can show that it's independent of the orientation. We had to pick one though. So the thing that we had to pick an orientation for is to locate cut points, to locate or to determine what the local orders are. And the question is, well, could you find a way to make those choices systematically that would give you the homology theory? We don't know if we can do that or not. We took for the code, which was Scott, Lou, and Heather and Aaron and I. We took the code that we wrote. Again, this is code that this is where we took Barnaton's program. And I didn't get into all of the details about how the program works. I was just trying to set up how you might approach modifying Barnaton's program in terms of getting these conventions to work. There's a bit more to modifying the code that we didn't get into in terms of calculating differentials and stuff. We'll have to just leave that for another time, perhaps. But we took the code that we wrote and we checked all the virtual knots up to 6 crossings from Jeremy Green's enumeration from his table. And we looked for examples that had trivial Jones polynomial and non-trivial Khovanov homology. We didn't find any. I don't know if this was something, I assume Khovanov probably did this back in 2012. But I don't recall, but we've checked it and there are none. We did go and look. Tubbenhauer gave a pair of 7 crossing examples of virtual links that have the same Jones polynomial, same non-trivial Jones polynomial, but different Khovanov homologies. And in that case, we've checked those examples and our results agree with his. In fact, the homologies that we get are actually the same. But because his approach is different than what Mantarov and Dijkester-Kaufman are describing here, he's defined everything in terms of cobordisms. And if you look at how he defines his maps and everything, things look a bit different. We still have the question of whether or not his homology is isomorphic to ours. We don't know for sure. We've checked a few examples, not enough to make anything like a conjecture or anything. We've checked a few examples, and in the examples we've checked, they come out the same. But it's an open question as to whether or not that's always going to be the case. And so with that, I will call it a day and thank you for your attention and say goodbye.